There's a lot of those in demo halls.
And not everybody is doing everything right. This project is cool.
It's supposed to win last year.
Yeah, sure.
So isn't that like the example we must all follow?
It is an example. And I'm not saying that they did everything perfectly, but they were overall the best project. Okay, well, let's get started. So recall that last time we did talk about how we can evaluate and how tasks works and how we transform abstract or concrete domain-specific tasks to abstract tasks that we can then later use to visualization. And so today we'll be continuing, first talk a little bit about design methods, and some of this is going to be pretty basic, and then we'll talk a little bit about evaluation. And I just want to say that I'm not going to do those topics justice, right? These are massive chapters with big research areas by themselves. And I'm just going to give you an overview on pointers and also pointers to other classes if you're interested in this kind of stuff. First, in administrative questions. We made the final project due the Wednesday before Thanksgiving, kind of trying to be respectful of people's holidays. But frankly, we're not going to look at them until the Monday after Thanksgiving. And so, do you guys want the deadline before Thanksgiving or the Sunday? Off Thanksgiving. Okay, so yeah, we can do that. I just I don't want to ruin everybody's Thanksgiving by having to work on this project. Who wants Sunday deadline?
Is it a competition? It's a competition, right?
What do you mean?
The there's best project.
Yeah, but this doesn't affect you. You can get a perfect grade and not be a best project. So not in that sense. Best project really only matters if you want extra credit. So everyone's the Wednesday deadline? 2 people. Okay, so do you guys mind if I do Sunday since the majority? Okay, so then we can push the final project deadline back to Sunday. Great, so let's talk about design methods. What is So what is design? Design is about creating something new to solve a problem, and that's just a general process, right? And people sometimes think of design as graphic design, but this is the same thing. Design is just an approach to identify a problem and then build something or do something to solve that problem. It can be used to make buildings like chairs, but also, of course, user interfaces and data visualizations. And you use it in many fields. All of engineering is basically about design. And the thing is that very often you have many possible users or tasks that compete at the same time for design. And so here's a nice video, and I'm not going to play this, but I just want to point you to it. This guy explains the design of a can. And it's surprising how intricate the can design is, right? You kind of have to, you want to minimize weight, you want to make it simple to build, you also want it to be pressure resistant, right? And so he goes into all the detail about how a can is designed, and so I would definitely recommend to watch this video. So design is not about just making things pretty, and it's also not about art. So art is really the appreciation of beauty or the emotion invoked, but usually you don't try art to be functional in some sense, but anything that you design has a function. So art is not without a practical, clear purpose, whereas something that you would design has one dedicated purpose or multiple different purposes. So it's art is about building without justification or evidence, and design is exactly the opposite thing of that. And you've all heard this phrase, form follows function, and the function can, of course, constrain possible forms. So the form depends on the task that must be achieved. Alberto Cairo, he wrote these couple of visualization books just recently, The Truthful Art. He says, to better define the goal of an artifact and narrow the variety of forms it can adopt. So if we really understand what are the constraints, there are we strongly reduce the space, the design space that we can actually that a product we create can actually take. One thing about design is it's a little bit different from, let's say, finding a mathematical proof to something. Design is really about wicked problems, and that's a term that's used in the literature frequently. And what are wicked problems? It's like when there is no clear problem definition, and when there's no clear best answer to that. Right? You can design a bridge in many different ways. All of them will fulfill its function. Which one is the best? That's not completely clear. So solutions to wicked problem are either good enough to fulfill the purpose or are not good enough. But there's these multiple solutions that exist, and they might have benefits in different ways. And then another thing about wicked problem is there's no clear point to stop with a solution, right? Like, do you have the perfect visualization? Do you need to continue iterating? That just doesn't exist. In contrast to wicked problem, you have tame problems, such as finding a mathematical proof, a chess game, or a puzzle. There there is an optimal solution, right? I have a state in a puzzle is it's complete, the state in a chess game it's won, the state in mathematics is proven. You might have seen this example of the Tacoma Narrows Bridge that's kind of all of engineering is a design problem, right? And so people built this bridge in the 30s, and it turns out that this bridge was designed but not properly. So they forgot the constraint of that they also have to calculate for aerodynamics of the bridge. And so when the wind was blowing, even not that hard, 60 kilometers per hour, 35, 40 miles per hour, this is what happened to this bridge, right? And so it had kind of an internal frequency that was similar to the wind speeds. And then what eventually happens, you can see how the surface bobs. And then finally the whole bridge collapses. And so the problem with this bridge were quickly known, and they were trying to find a solution. And they had done wind tunnel experiments with this bridge and had proposed solutions, but they were not implemented on time. So clearly, here, this isn't a satisfying design solution in that case, and that's been studied in many contexts. So why does design matter for visualization? Well, of course, we can combine visualizations to solve problems that are super ineffective. We have users with unique problems and data. We have a huge variety of tasks, and we have this large design space of different visualizations. And so one thing that we tend to do, especially if we ourselves build something, is that we are a hammer in search of a nail, right? And so one of the pitfalls of visualization design is this premature design commitment. This little guy thinking here, of course, they need the cool technique that I built last year, without really thinking broadly about what is the problem. And so this is kind of Tamara Munzner's analogy of how you should actually design a visualization. So you have the design space here where all of the different visualization solutions are. This is kind of the absolute universe of all possible solutions. And you have your own technique here, and you might think that this is a good solution to a problem. But then what the argument here is that you need to broadly consider options. And so to be able to broadly consider options, you first have to know as much about the design space as possible, right? So like before this lecture, before you took this lecture, you might have heard of like 4 or 5 different visualization techniques. By the end of the semester, this space of things that you can think about might be much, much bigger. So you might be able to find better solutions to a specific problem. Then you might kind of like consider a subset of these problems because you have kind of excluded some options for various reasons. Then you propose 2 solutions to your users that you work with, and then finally you pick one. And notice that this isn't the same one that you initially had thought might have been the best solution, right? But just by formally considering all of the possibilities, you might arrive at something different than what you started off with. And so the idea here is really to think broadly about what are the options before you pick one particular design path. And so then now I want to talk a little bit about design methods. And so there's like, this is going to be like a rapid overview of things from requirement elicitation to like, this is how you actually sketch and prototype designs. And so like what we do in our lab is to kind of like understand the main goals and the requirements is these creative visualization opportunity workshops. This is a method that one of our PhD students who has since graduated has developed over like multiple years. And so like this is kind of a way of getting a lot of stakeholders in the room for like an extended period of time between like 3 hours and the whole day, or sometimes even 2 days. And then run a workshop with them where you have like different kind of components. Some of them are like probably familiar to you, such as like brainstorming, but there are some more formal ones like an analogy introduction or visual thinking, like if you had, like what are the things that you could do, what would you like to know, what would you like to do, what would you like to see with your data. Or things like barrier removal, right? So like people think about their problem, but they always condition it, well, I can't do that because of that. And now you can like run an activity saying, assuming this barrier doesn't exist, what could you do? And so these workshops, there's like this website here that you can use. There's also a paper there, but this website allows you to build these custom workshops and has these kind of like descriptions of activities that you can kind of like customize to your problem. And we've been using this in like probably 10 projects in the last 3 or 4 years, and they've always been very successful because we got like a lot of it out in a very short time. And if you do this like a more traditional approach where you just keep meeting with your stakeholders every week or so, then you end up like spending weeks and weeks and weeks, but never really get into like what you really want to do. And so the output of this are some things like actual artifacts. So what we often do is have people like write down concepts or ideas and post it and then arrange them on big flip charts. And what we do then is we take this home. We also sometimes audio record the whole thing, and then we do some qualitative coding or some analysis to understand what are the main themes that came up. So here's an example of one of those creative visualization opportunity workshops that we did at ARAP, this reference lab here in Salt Lake City. Here we have a couple of like medical directors that make diagnosis for like genetic diseases, and then some bioinformaticians, and they're all in the same room, and they're kind of like thinking through the analysis problem, and you see them here arranging their ideas by topics and importance. Okay, so like this is kind of like one requirement elicitation technique that's one that I would recommend. Of course, there's many others. I want to switch gears a little bit to talk about how we actually design something. So one of the things that if you've ever taken a class that is about graphic design, you might have heard the idea of parallel design. And that applies also to visualization design. So like what you want to do is you do not want to kind of like iterate on one idea, but you want to really try to be broad and try 2 or 3 different versions first. So this is from a paper where they ran an experiment which for graphic design, what leads to better graphic designs? Is it like a serial iteration over some steps, or is it parallel iteration where they force people to actually do this parallel prototyping? And so you see that in the serial iteration, like people kind of got stuck on the first version, right? So they kind of iterated it, but it doesn't necessarily make the best use of like the whole possible design space. If you had this parallel design, then you can see there is like much more iteration between them, and then you could argue that this here is a better design than this flyer here. So parallel design is an important piece that you should always try to use when you design also a visualization. And then there's a couple of methodologies that kind of combine this requirement and analysis and this kind of design, this parallel design idea, and then also a convergence step into them, into all of them. So this one here is the 5 design sheet methodology, which was published by Roberts and some of his colleagues. And so they tried this in classrooms, but also in visualization projects. And so here they have like design sheets are about brainstorming solutions to a task. So this is kind of the requirement analysis step. Then they have 2 to 4 different principal designs. So this is the parallel step here. And then they converge on a design to implement. This kind of like is just a formalization of what I just explained. And it can be useful if you like run a narrow project. So there's also a website that explains this methodology in some more detail. And then this is also useful in a classroom context. If you're not completely familiar with visualization yourself yet, I need visit cards. This is another project that was published at Viz, where you have different types of cards: domain cards, inspiration cards, abstract cards, and layout cards. And that you can kind of like use to kind of like structure your process and help you design, compare, collaborate, and apply and synthesize like the design process. So like once you know roughly what you want to design, how do you now get to actually like producing a sketch before you start implementing it, right? So one thing that you can do is wireframing. So wireframing is basically you like build a prototype, either just like like an inactive prototype or an interactive prototype, and you can use dedicated tools like Adobe XD or Sketch to create those wireframes. And there you can also like emulate some interactivity. In practice for visualization, those tools don't really like let you encode data, and so that is always a little bit tricky. So these tools are really designed for things like websites and like traditional user interfaces, but they don't really you can't really map data to something, so you can't really like prototype with data here. What you can do just for like basics is also like using tools that you probably already use, like PowerPoint or Keynote or Illustrator. Those are kind of useful because you know how to use them. You can get something that looks good fairly quickly. And so some people that I know, some students, they create like pretty complicated slide decks where they show all of the different animations of their interface before they implement it. And then if you need to prototype with data, you could use a tool like Tableau that allows you to simply like create plots but with the real data, right? Where you can kind of see what is actually going on. Or I know that people like Amanda Cox from the New York Times usually prototype with R and ggplot. So and then converts that into like web-based interactive visualizations. I kind of like recommend those things with a grain of salt because I think that they are not quite as like they take a lot of time and it kind of tends to lock you in into a specific idea. So I personally am a big fan of hand sketches. And so, like, here are a couple of examples of hand sketches that we did early on in the process and how they then, like, materialized in a real system. So this was kind of like an idea that I had for this upset tool, which we'll talk about in the set lecture. This is the very first idea that I drew on the whiteboard talking to one of my co-authors. And then I had, like, a pretty primitive hand sketch here in my notebook. And you can see that, like, it doesn't exactly resemble the final product, but you see like the main idea of all of this stuff here is still in here. And so that can kind of like guide your design and your process, but just like hand sketches are super fast and work well. So here's like an example that Jen did. One of our TAs, she started, like this is a project for phylogenies. Yeah?
I was going to ask, when you're doing hand sketches, I have issues with showing interaction, and that's sometimes pretty key to what you're trying to draw. Do you have like things that you do for that?
That's tricky, right? Like I think my recommendation now would be if you have interaction is I would use something like an iPad, and then you can easily copy like your sketch and then have different conditions for it. Like otherwise, you have to do something more fancy like animations in Photoshop. But for hand sketching, like it really depends a lot on what you want to animate, right? But usually not. These are mostly static. So here's like a two-part design process. This is Jen, and Jen is like an Illustrator expert. And so she started out with a hand sketch. And then this, you won't believe it, this is an Illustrator sketch here. And it looks like a full-on implemented interface, right? But she really went into the details here and ended up like the implementation here resembles the sketch to like a pretty large degree here. So that's like an extreme example of how detailed a design can be. And then this is kind of like a project that Kerry did, and here she uses a lot like sketching on iPad, which I think is kind of like the most useful thing nowadays because you can actually copy stuff and you can also like add artifacts, screenshots, and combine them and modify things easily. So you kind of like have the power of both computers and the like flexibility and ease of use of hand sketching. And so here's like an initial design that kind of was eventually then implemented in this tool, but she also uses these same kind of tool sets to do design reviews, right? So there's like, she just loads a screenshot into her iPad and then we go over like, this isn't working, or here we need to draw something on top of it, and so on. So that's also very useful. One other idea, especially like to kind of like really test out before like a big system, to kind of like do almost a user study before you start building something, is this interactive prototyping. And traditionally, this has been done like with paper prototyping. So people build an interface completely on paper, and they have little snippets that they can kind of dynamically replace. And then they show this interface to users, and then the user says, okay, and now I want to click here. And then they actually reshuffle the paper or give them a new page, and this way to evaluate whether this is intuitive or useful for them. You can do this also digitally, but this paper also studied, like if they do this digitally or on paper, people tend to be a little bit more open about saying what they think and giving their own personal opinions. If you show them something that is clearly low fidelity prototype, people tend to think if you show them something elegantly, like an elegant wireframe that is clearly computer rendered, they think this is already the final prototype or the final product, and they tend not to make as many suggestions. So the hypothesis that those people came up with is that paper prototyping stimulates creativity and interaction. But of course, for visualization, this is kind of like a complicated and tedious process. And just some other methods that people use to design is like, of course, interviews and observations. So like you could do interviews. What we also usually recommend for like a long-term design study or long-term project is to really go into a lab and be embedded and observe how people use it. You can do some qualitative analysis of all of those, like the outputs of all of this, so that you kind of like identify any recurrent themes. One thing that is useful, especially if you're designing for user groups that you don't have like physical people for, is you can come up with personas. And so you define like, hey, these are my 5 different types of users. And then you write down what are their goals and what are their needs and what is their background. And then always keep these personas in mind when you're designing something. You can do data sketches, like what I mentioned earlier, for example, using some like easy plotting library like Tableau, or like Matplotlib or ggplot to kind of like get started with something, or use one of those interactive visualization tools like Lyra, where you can kind of like prototype something quickly. And then, of course, you can always do coding. Like, you can really do something quickly if you completely disregard any code quality. And maybe that might be useful, but then you should also throw it away later, because refactoring might not be like a good strategy. Okay, any questions about design before I move on? Great, so like once we have built something, how do we know that it actually works? Well, we can evaluate. We can evaluate it. And so we talked about different types of evaluation already. We talked about the nested model, but now we'll go a little bit more into detail. Here's a paper that I definitely recommend reading. This is kind of like a nice, like non-pretentious introduction to the whole area. It's kind of like evaluating information visualizations by Sheila Carpendale. She kind of like discusses the design space of evaluations and what each of the methods are good at. So I'll give you a little bit of a taste of this now. So, like, what is the role of evaluation or validation? So, you want to avoid ineffective solutions by, say, identifying them and dismissing them, but you also want to justify your solutions by having some data that they are actually useful for what you claim they're useful for. And so the dimensions in like what you want to validate depends a lot on like what are you actually trying to show. Especially within visualization, we distinguish between like perceptional aspects and techniques or systems aspects. So for example, there's a lot of like vision sciences and that is almost psychology happening in visualization, where we try to evaluate, is it better, like can we read like the angle in a pie chart more easily than the size of a bar, right? This isn't really like a visualization systems evaluation. We are trying to really understand some basic perceptual properties. Or if you want to ask the question, is my visualization system any good? This is completely on the other end of the spectrum, right? So like you've built a complicated interactive system that works in some situated context. Now you want to know, is it any good? So you like you clearly like you don't want to use the same methods to or even the same standards to evaluate those two things. And then the other dimension that you have to think about is like what you create or what you want to validate, unique, or is it a comparison? So if you've built like a complicated visualization system for a domain collaborator, you're not going to build another complicated visualization system for your domain collaborator and then compare those two to see which one is better. But if you like are again in this perception space, you can easily do comparisons. Or if you have something like you propose an alternative to like parallel coordinates by saying I do radial coordinates. Then you have a clear comparison target, right? So then you definitely want to compare. And then something that doesn't give us doesn't evaluate whether something is better or not is usability testing. Usability testing, it really doesn't try to make any claims of how good something is compared to anything else, but it really is about checking for problems in your system that you can fix. And usability testing can be quite useful to do even informally with like 3 or 4 people, observe how they do something, because when you design something, you will find that you know exactly how to use it, but as soon as you give it to somebody else, they will fail using it, especially for the first couple of times. So let me give you one example here. This was a study that we did where we had tried to these linking techniques for highlighting. I showed this in the perception lecture, but here we did a quantitative comparative study where we really wanted to compare the perception of those 3 different techniques. So just highlighting, highlighting with this fancy routing, and highlighting with the links that are basically just straight lines. And so we ran a control experiment here where we did both eye tracking, but also measured time and error rate. And we then reported, like we had a hypothesis. We said like our hypothesis was that visual links lead to better performance, are faster than conventional highlights, and then context-preserving visual links do not have a negative impact on correctness. And so these are hypotheses. We did some statistical analysis. And we did actually find that these hypotheses were true, and then we kind of report here on search time and misestimation. So what, like, side note, these charts are really clearly not ideal. I wouldn't do this again, but in 2011 I didn't know better. So like this was like a classical quantitative experiment. We had hard data. It was very controlled. People came into a lab. They had introductions and they performed this task. Everything was measured. Everything was timed, and so on. We also did like eye tracking on this data, and so we ran like this was kind of like trying to give us a little bit more context. And I would say eye tracking, the way we used it back then, was really quantitative data, but more qualitative data. So like these are the different gaze plots for the 3 different techniques of how people actually looked at this. And so though we weren't able to like quantitatively say anything about that, I think it's pretty obvious that you see that people just like look at way more like randomly scanned areas compared to like these 2 here, where they kind of follow this big tree consistently. And eye tracking has also come a long way since then. Nowadays, you can actually do quantitative analysis with eye tracking by defining regions of interest and measuring how people look exactly where and so on. And on the other extreme of like an evaluation approach that we did is this kind of like case study. So here we built this intricate, complicated system that was designed especially for this group of researchers that were studying the genetic underpinnings of suicide. And like we couldn't run like a quantitative study on this, right? Like what would we ask and what would we compare it to? So on the next slide here, I'm showing what they're currently using. And sure, we could have like given them like some complicated tasks and then run a comparative study between the 2 of them, but there's like so much that you simply cannot do with this particular tool that it seems like wasted effort. So you can, what we did instead is we like described the case study. And so we said like exactly like how are people using it, and like by observing them, and they would actually explain how is their analysis process and what are their findings, and why are those relevant in their domain, and what are the next analysis steps, and so on. And so they basically wrote like a 1-page report on exactly why this tool is useful for a specific case, and what they actually found for a specific case. And so that's like kind of a common method to do evaluation. So this is kind of like an existence proof, right? You can use this tool to successfully find something. And that's sometimes the best you can actually get. So kind of like reflecting on this a little bit, and then I want to also like move on to some other techniques. You kind of like have this, these different methods, and there's many of them. But mostly like what I want to point out, and I have another slide about this, is you have this spectrum between certainty about what causes any differences that you observe. Like if you have a controlled experiment in the lab or in a crowdsourced approach, versus ecological validity. Like if I run this comparison between like which, like is a bar or the pie chart easier to perceive, does this really translate to how people use those charts? It's not clear, right? Like we know exactly that the variation in performance is due to this, what we had in our experiment, because we very carefully controlled that it can be nothing else. So we get like high precision, and we have a certainty about what causes the differences, but we don't get any ecological validity. But if we use something like field observations, where we study people using a tool in practice, or case studies, we get high ecological validity. We can demonstrate that this is useful in practice, but we can't really say what was it, right? If you build a tool that does like 50 different things, what of those different things was really what made the difference? You cannot really tell. And this is a bit of a problem for like, can I transfer like knowledge that I generated in such a project when I use a case study? And so in the middle here are things like interviews and questionnaires, or field observation, lab observations. Other things that you can do is, of course, like if your contribution is like some improved algorithm, you can do like algorithmic performance measurement, and that's of course like if this is your claim to for your contribution, this is kind of the best way to do that. Another approach is heuristic evaluation. where you kind of like judge the compliance with some recognized metrics or usability methods. And so people have actually established a protocol for heuristic evaluations, like a standardized questionnaire that you send to an expert your visualization technique and this questionnaire, the standardized questionnaire, and then they will rate the visualization techniques. And so you get kind of like this expert, like a mix between expert evaluation and heuristic evaluations, because you assume that your experts judge the compliance with recognized metrics. Who's heard of think aloud tests? Okay, a couple of people. So think aloud tests are like useful for usability testing, right? You can't use a think aloud test when you're also measuring correctness or performance, because those are not, like, they will influence each other. But in a think aloud test, you give people a task and ask to verbalize what they're thinking and what they're doing. And so, like, oh, I'm gonna like navigate to this menu here to see what I can load this data set. Oh, I see here is an outlier, and so on. And then you can like video record them and what's happening on the screen, and then later analyze what is going on to identify any problems in the process. And so this is really like a usability testing method. Who's heard of Wizard of Oz experiments? A couple of people. So Wizard of Oz experiments are pretty cool, because the idea is that you can test and evaluate something before it exists. And the way this works is that you give people a system, they do put in something, like give some input, and then the system responds in a magical way by giving them the right answer. You can, for example, people have done this, like, how do you sketch which visualization technique you want to see? So people like sketch the scatter plot, and then the system will automatically generate a scatter plot for them. But of course, building a system like this is hard. And so a Wizard of Oz experiment has a human actually seeing what you're doing and then giving the answer or preparing the answer. So in the case of a scatter plot, somebody would sketch the scatter plot, and then the human would select scatter plot and show them the scatter plot without the subject seeing that, right? So the subject thinks the system works, but in reality, it's just like a human doing the hard part. And so that kind of like allows you to test things that are difficult to implement, for example. I talked a little bit about eye tracking. I talked about expert evaluation. And then there's this other method, insight-based evaluation, where you kind of like observe somebody along a think aloud experiment, and then you have like, you classify insights, like what they learn from analyzing the data, and there's like multiple different types of insights, and then you can keep track of it. And so the idea here is really that you get something very sophisticated, like that you kind of like can test, like have a quantitative test for like a pretty sophisticated system. And then of course, if you deploy a tool, you can do log file analysis. So how are people actually using it? And so this is like what happens a lot on websites, right? If you go to Amazon, they track everything you do, they analyze what, like, they do A/B testing behind the scenes by looking at log files. Yeah?
You mentioned for think aloud testing that it can influence correctness of tests.
Yeah.
Can you go into that a little bit more?
Well, so if you kind of like change the natural way of people interact with the system, right? So like people might like just behave differently when they have to externalize everything that they're thinking about, and they will certainly be slower. So you can't really use like this as a data, like a think aloud experiment at the same time as when you're trying to time them. And you probably should also not look for correctness, because like it's just not the way they would naturally interact with the system. Okay, so what are the kinds of metrics that you look at when you try to do evaluation? So there's like these like objective metrics and subjective metrics. Things like task completion time is like a common one. Errors, percent of tasks completed, ratio of success to failures, numbers of repetitions, numbers of command use, number of failed commands. Then you can also like measure physiological data, heart rate, pupil dilation, gaze movement, or anything like that, or number of insights. And then subjective metrics are like what do people think about a system that they use. So like ratings, rankings, user satisfaction, subjective performance, ease of use, intuitiveness, judgments, comments, and feedback. And so like I really like recommend even if you do something quantitative, you always also want to do something subjective afterwards. You want to have like a couple of survey questions, but most importantly, you want to interview people about like what was their experience with an experiment, because this is where you get a lot of like interesting nuggets and things that you didn't really think about when you designed your experiments. So if we look at this quantitative versus qualitative evaluation, we get kind of like quantitative methods give us like objective metrics and measurements, and we can use some statistics for interpreting the data, whereas qualitative methods are really like subjective metrics, like descriptions of situations, events, people, interactions, observed behaviors, or you use direct quotations about people's experiments, attitudes, beliefs, and thoughts. And so, as you can kind of like guess from this type of answers that you get, like you can get like much more interesting things out of qualitative methods, but of course it's going to be harder to quantify and make like a hard argument of is A or B better. And so this kind of like goes back to this what I mentioned earlier, this a controlled experiment versus like something that is in the situated environment. And you can also think of this as internal versus external validity. So internal validity is, can you trust your experiment? And of course, internal validity is high when tested under a controlled lab condition. And then you can make sure that anything that you observe are due to the test conditions. External validity is the question of, is your experiment representative of real-world usage? And this is kind of like high when the interface is tested in the field. For example, if you observe how like visitors or kids test the handheld device in a museum. And so then you can say that my results are valid in the real world, but it's much harder to really like say this isn't just some random variable because there's so many other factors that go in here. So you kind of like always have this trade-off. The more akin something is to real-world situations, the more the experiment is, of course, susceptible to uncontrolled sources of variations. And so depending on what you're testing, you kind of like have to accept this trade-off here. Yeah, so basically this is just a recap of like how you can use all of these evaluation methods at each of these stages of the design process. And so I don't want to like restate this here in detail. I just want to close this section of the lecture today with this this quote from Jaak van Wijk. He gave a capstone at this in 2013, and like, he was actually arguing against any kind of evaluation. And he was basically saying, you should develop new methods, interfaces, or software that are so awesome, cool, impressive, compelling, fascinating, and exciting that your reviewers, your colleagues, and your users are totally convinced just by looking at your work and some examples. And that's kind of like an interesting perspective, and I partially subscribe to that method because like sometimes you just want to show something that is so much cooler than anything else. But of course, it's not necessarily like a rigorous scientific approach, right? So like there's always this trade-off intention there. Okay, so any comments or questions before we move on to maps? Okay, so now for something completely different. I want to start this off with a little exercise. Like this is going to be fast, only 5 minutes. Here I have 2 maps, and I want you to talk with your neighbors about why like these maps are not great, and I want you to figure out why they're not great.
I know it's a story. Like when you realize that,
I had that problem. I tried because of the size of the yeah, I have two.
Okay, so what are like any of the problems to be identified with this map here on the left?
Dirt doesn't vote.
Dirt doesn't vote. Yes. So what do you mean by that?
So this is by land area, but not by population. And population is very, very non-uniform.
Yes. So yes, that's clearly the main problem here. Like if you do like something like this is called a choropleth map. We'll talk more about it. You kind of like assume that size of like the geographic region that you're looking at corresponds to the data that is underlying. And so that's why people like President Trump really like showing the map of their amazing victory like this, because basically it's like one massive red map, and kind of like people vote, not land, not dirt, right? And so what's the problem with the map? Or anybody else have any other comments about this map? Okay, so what's the problem with the right one?
It's skewed. I don't think Antarctica.
Yes. So Antarctica isn't actually bigger than Eurasia. Or Greenland isn't bigger than Africa, right? Why is that?
It's Mercator projection.
Exactly. So we have, what we see here is a Mercator projection. And Mercator projection has like optimizes for certain criteria like angle, but doesn't do for others. And so we'll talk about those two different aspects and many more today. So if we take a look at this map again, so here, like this was, you can actually, like here is a comparison of the popular vote as a bar chart. You saw that Bush had 62 million votes and Kerry had 59 million votes. But if you count like how many square miles are colored red versus blue, you see this massive discrepancy here, right? So this is about like 5 times as much red as blue because it doesn't account for the dense urban areas. So, like, what are maps? Maps are a special type of spatial data, right? We can have like all kinds of spatial data, like from a CT scan through like the simulation of like the galaxy. But like maps, and especially if you think about maps on Earth, this is like this very special type of spatial data that is very important for us as humans because we move around in that space. And so you should use maps when what you want to show is really all about spatial relationships. Like if the spatial relationships between different data points is what really is the point of your visualization, then yes, please go ahead and use a map. The task that you want to be able to do on a map is to find a location, find a feature like a county, a country, a city, or a street, find a route between A and B, how can I easily navigate, or if you talk more about data visualization, like this is geography, GIS, right? If you talk more about data visualization, it's about identifying attributes associated with the location, such as the elevation at a specific position, is it land or water, or what's the GDP of the country that you're currently looking at, or any other attribute of like a city or a county or a state. And you want then to be able to compare these attributes between different locations or between different features. And like the one question, this is kind of like odd to say in a map lecture, but I want to start out this lecture by asking this question: do we really need a map? And more often than not, the answer is no, you don't. Like nobody needs to, nobody who like consumes, let's say, American media needs a map of the United States to understand where like Massachusetts is or Texas, right? Like you don't actually need to show this on the map. And by like not using a map, you actually have so much more power to design. So if you try to do this, like we looked at this, how states have swung over time. If you try to do this in a map, this would be horribly difficult, right? Like you would have to have very nuanced color encoding and then some animation. People would have to really be very careful. You would have the problems that we just talked about with like states being like not proportional to their population. So like if you can avoid it, just do avoid it. Like maps are good context, and especially useful if something isn't super familiar. But if you're like trying to visualize data about the 50 states in the United States, you do not need a map usually. Here's another example. This is like the 2016 election where you see Clinton versus Trump for certain battleground states. And so what this shows here, is both like the margin, the projection, and some uncertainty, right? But doing something like this uncertainty quantification on a map is almost impossible. And so by just like taking away the spatial context, you can do something much more powerful, can communicate things like uncertainty here. But For the rest of the lecture, I'll talk about actual maps and not go on rants why you shouldn't use maps. Map projections are, of course, the problem with maps is that we are trying to visualize usually on a 2D screen or paper something that isn't 2D initially. So the Earth is like a flattened sphere, and we need to unfold or project the hull of the sphere onto paper screens. There are globe screens, but they're not very common. And so what are the kinds of things that we would care about if we were to do this projection? Obviously, I can never do this perfectly, right? I can never perfectly unroll a sphere onto a flat sheet. So I will always have to make some trade-offs. And so here are some attributes that you need to consider when you create a projection. It's like the area, shape, direction, bearing, distance, and scale. And map projections, the variety of map projections that are out there, is really just different compromises according to those different attributes here. And if you haven't seen that yet, definitely look at the XKCD, what your favorite map projection says about you. That's just a lot of fun, and you learn something about projections as well. So the simple solution, of course, is to use a globe. Then you don't have to actually use any map projections, but and it's actually cool nowadays. Google Maps wasn't able to use this a while ago, but you can actually use Google Maps as a globe, right? And you can show satellite image, and the satellite image actually also has live clouds here. So clearly, this is kind of the way to go if you have an interactive system. But still, this isn't particularly useful if I want to compare, let's say, economic inequality across the globe, right? Because I can only see part of the map at one time.
So can you just have two globes?
You can have two globes, but you will still not, you need probably 4 or 5 globes to get a good representation working. So because here on the edge, Alaska is on here, right? But you kind of really want to scroll this way to see it properly. So you need a couple if you wanted to. Yes, that would work. And there are kind of approaches like this out there. The other extreme is the Mercator projection. Right? The Mercator projection is this very well understood and widely used projection that was kind of one of those that showed the second map on my opening slide. That was developed by Gerardus Mercator in 1569, and it's a projection of the sphere onto a cylinder. So it's just really exactly projecting each position out onto the cylinder. And the benefit of this is the angles are preserved. And so lines of constant bearings are straight lines, and constant bearings means that you can use this for a constant compass heading, and your constant compass heading corresponds to a straight line on a map. So if you want to navigate by sea, for example, or also by land, this is kind of a good map, right? But it's not it's developed for sailors, but it's not a good map to show geopolitical differences in health or something like that. And so this is the example here where you see Antarctica being this huge landmass and Greenland being this huge landmass. It does also preserve circular features. So here this is a Mercator projection of the surface of Mars. All of the craters remain circular. But of course, this Mercator has its uses, but it's also problematic, especially when it was used to teach geography, which I don't think it is that much anymore. It kind of is this massive distortion of area that is distant from the equator, and it's unfair to the global south, making places that are mostly trees, snow, and better off white people look huge, and the places where most of the world's population live look puny. And that's of course because there's a lot more land mass north than south, and so we also even tend to clip maps frequently like that.
Isn't this exactly the same though? It's near the equator. Because if you go south enough, then...
No, there is a lot more land mass that is north, but there isn't equally much south, and a lot of people live actually around the equator, right? And so that's kind of the problem here. And I really like this quote is, Mercator works really great if you say Ferdinand Magellan looking for a compass bearing that will take you around Cape Horn, because all the latitude and longitude lines and angles in between lay out nice and straight on the map, like we experience them in real life. It also works well if you Google and you want a map image that you can neatly slice up into little squares that your server sends to a customer's browser. North is always up, your home time doesn't look squished or slanted when you zoom into it, and everybody's happy. But then you have things like that, right? Especially, like, this is something that you might know, but if you think about it, you don't actually realize, right? That Africa is bigger than the United States, Western Europe, Argentina, India, and China combined. It's just not how we think about space and how we think about countries on a map. And so here is a map of Mercator, like a Mercator map juxtaposed or overlaid with like how big those countries really would be. And you can see that especially Canada, Greenland, and Russia are disproportionately overrepresented on a Mercator representation, whereas like the African countries, and like there isn't really all that much in the south here, right? So this is just like a strong distortion effect that is problematic. And you can kind of try this on your own by playing this game here. This is a Mercator puzzle. And let me zoom in a bit. Okay. Well, anyways, you need to place these countries correctly, and you can see the effect of the projection, right? And so the one that I picked here is actually fairly easy, right? Which country is this?
India.
India. So we can place it, and then it clicks in green. What do we have here?
Oh, that's South Africa.
South Africa.
There's a little hole.
And look at the difference, right? If it were like in South Africa is about the size of Greenland. But we can click it in here.
Yeah, move up. Yeah.
Yeah. And then there's some more complicated. This looks like France. No, Spain. No. Poland. No. Yeah, I'm not gonna solve. It's actually fairly tricky, especially if you like start doing lots of smaller ones. But anyways, like play around with this to get a little bit of an intuition of what the Mercator projection does to geometry. The caveat here is this is really like only a problem if you look at the maps of the world. If you look at a map of the city, this isn't an issue, right? And like very frequently, when you want to use maps at a much smaller scale, so then distortion isn't the problem. So we can actually use the Mercator projection if you want to do some like visualize Utah, and you're probably totally fine to do that. The other thing you could do is just to use latitude and longitude to project, right? But this doesn't preserve angles, it doesn't preserve areas. Things are squashed at the top and the bottom. But that's something sometimes quite convenient, right? Because you can just, like, you don't have to do any projection, you just take them geospatial data, and just by mapping it by that long, you get a rough outline. And then there is these azimuthal projections, where you project onto a plane that is tangent to the Earth. The angles here are correct around the center point, and great circle through the center are straight lines. The radii correspond to the distances. And you sometimes see something like this in an airline journal, like an airline in-flight magazine, where you see like where they fly based on from their hub, right? Because this is kind of like you focus on one point, and from there things work out quite well, but not necessarily between other points in the map. Here's an azimuthal equidistant version in D3, and here's like an example of like from a magazine from like the 60s or so, of where their reporters are traveling around the globe to report on your latest stories in Time magazine. The Winkle triple projection is a modified azimuthal map projection that is also averaged to a cylindrical projection, and that kind of tries to minimize three kinds of distortion, like area, direction, and distance. And this is kind of like the projection that is nowadays used if you like show a map of the world for educational purposes. And this is like for maps of the world. It's been endorsed by the National Geographic Society. It is now what is used in textbooks, and this is what this looks like. And so this gives you like a bit of a sense of like this is a globe. It doesn't like disproportionately increase the size of any of the northern land masses. And if you like were to plot a circle, you can kind of like understand how the distortion actually works here. And you can see clearly that there is distortion, but it is a little bit more controlled than in the Mercator projection.
Why don't they write textbooks in like D3 and have a globe?
Well, that is an option nowadays, but not a couple of years ago. And I think you will see more of this, right? Like interactive stuff where you don't have any of those problems. And I'll give you examples later of how you can actually optimize your projections to your tasks dynamically. Always equal area is area correctly, but distorts distances and shapes. And this is like what we frequently use if we show a visualization of the United States. And then, like to this point here, you can actually, depending on what you're trying to do, you can pick the right projection. So this is a project, and actually, like Google Maps does this now, right? So if we do this Google Map, if we zoom in here, like switching back to a map here, like this is clearly not a Mercator projection, but if we zoom in, it switches to like a Mercator projection without us really noticing. And this here just makes this a little bit explicit. So here we have this projection diagram, and I basically can navigate around here, like where is my focal point, and then how far do I zoom in. And depending on how far I zoom in, it dynamically changes the projection. And so let's pick some landmass. And then if you keep going in, we see that it again switches like the projection, and finally at like a very detailed level, it kind of straightens it out and switches to a Mercator projection. And around the poles, they use like a specialist Lambert azimuthal with a polar aspect. So you can kind of like dynamically interpolate between all of those different projections, and that's kind of like a neat way of doing these interactive, these computer-based visualizations. And you've seen projections, of course, in our projects. There's like many projections that are available in D3. I'm not going to go over them, but there's like standard ones, and then there's extended ones, and you can pick the one that you think works best for your particular case. And then, like the other idea to like unfold the Earth is kind of like to do the orange peel approach. This is like using small patches and showing the kind of tear lines is one way of visualizing, like unrolling the Earth. And this is actually so here's a video by Wireframing, the guy who did the squarified tree maps. This was a cartography paper that he wrote about different ways of unfolding the Earth with these kind of like orange peel principle. And so you see first some geometric options. But you can also use geography to kind of like define where to tear something up. And so he later does like guarantee or like make sure that this breaks up only where there's water. So like this. But you can also do this the other way around by breaking up things where only where there is land, which is kind of then not very intuitive. Thus, but yeah, in principle, that's possible.
Is there like a soccer ball one?
Yeah. Okay, so here is like a link that you guys can look at home when I post the slides where there's more information about map projections. Now I want to like briefly talk about some map software, navigation, and then move on to actually data visualization on top of maps. Basically, like there's like many tools out there, but the data usually is from like things like OpenStreetMap, Google Maps, or Apple Maps. These are kind of like the big data providers nowadays. OpenStreetMaps is a community-based effort, and so you can actually get the data. Google Maps, of course, like everybody knows. And so you can like do visualizations on top of those. They're super useful for navigation. So for example, here I'm plotting the path of like going to Porcupine after lecture. And so you have two different representations here. You have like the spatial representation, but you also have this abstract representation here that just gives me some like guidelines where the spatial context doesn't matter as much. If I take a bus, I really only need to know I need to get into the bus, like I need to find the bus station, but then I only need to know where I will have to get out again. And so that we have this continuous, or these discrete states here, actually abstract and specific. But actually, when people draw maps, like we don't do this that much anymore, but like 10 or 15 years ago, if you ask somebody to come to your house, you would maybe like sketch something like this for them, right? But what you would do is you wouldn't try to do something that is completely accurate in the map. You would kind of like have some landmarks, and you would kind of abstract away things that aren't important. And so there was a project by Microsoft that kind of tried to do this for navigation. And so here is an example to navigate from Madison to somewhere, I guess in Michigan, somewhere around the lakes anyways. What they did is to kind of like try to summarize it as a human would draw it. And so you start off like here on US 151, then you go on US 18, then on I-90, and so on. And so this is like there's much less information in this map, but it might contain all of the information that you care about when navigating. And this was actually implemented in one of the early Microsoft maps, and so you could actually get directions like this back in the day. Nowadays, this is of course all gone, and so no current tool like this exists. Okay, so this was just like a 2-minute overview of some of the tools and some of the ideas about mapping. Now I want to start bringing data into the picture. And so the simplest thing that you can do is direct mapping. One data point is one pixel, and you might color code this. So here is a visualization that does exactly that. This is easy to do with like a map interface like Google Maps or OpenStreetMap. They have these markers, you just place them. This here is a map of, this was kind of done after like a school shooting in New Jersey, I think, yeah. Or Connecticut. And what they did is this is like a group of journalists did that, and they scraped the public database of gun ownership and put this on the map and then published this on the internet. And so you could actually zoom in and look at, does my neighbor own a gun? And you can imagine that, like, yeah, it was Connecticut. So this was published after these Connecticut school killings. And I guess like what I wanted to briefly talk about here is it okay to do this? So why and why not? Like the data is public.
So like my first thought is like guns are generally a high value item. So you're really making your people who own guns targets for burglars. Now we don't need to think about the work rate of
That's an interesting perspective, yeah. You could also say this is a dangerous territory for burglars.
Yeah, kind of like along the same lines, like it's really, like with a visualization like this, and with data that has such high fidelity like this, it's really easy to use something like this to cross-reference with other stuff to gain even more information about people at particular addresses.
Mm-hmm. Yeah.
There's like a sort of legal phrase called reasonable expectation of privacy. So you might be like, throw something out and like put it in the trash. You don't really expect people to be digging through your trash. So sort of similarly, there's sort of a gradient of how public some information is, even if it's like
Yeah, exactly. Like this is like just because some data is available, right? It's not necessarily accessible to everybody and easily. It's kind of like It's not the same as having like a database where you can look up a specific address and get an answer of what is this address, where there is a gun registered at this address, and showing it like this, right? You kind of like making it much more accessible. Anybody think this is absolutely fine and this data, this is public anyways, why should we bother? Why?
Well, I mean, all you have to do is combine the data with the map, and then you got it.
Okay.
To me, it's less of an issue of having this tool, if you will, available, and more of an issue of the timing that the tool was published. Because it seems almost intentional that it's pointing fingers or saying like, these are the problems, this is why there's a school shooting, which, I mean, whether you believe that politically or not, that's irrelevant to the shooting itself.
Yeah, that's a very good point too.
Do we have to like invite someone from the English department over there to tell us whether or not we should be building this or not?
Well, I think that like I want you to really think about whether you should be building something like this, right? You can do lots of stuff with technology, and like visualization isn't immune. Like people think about ethics in computer science, mostly like algorithms making decisions, right? But it's not just that. It's also like things like that where visualization is like you can actually do stuff that you maybe shouldn't do, and you should think about your reasons for doing them. And like you could make a similar point just by showing like how many people do own guns without like actually giving people's addresses and like, revealing that information. And that was a big scandal. There's a blog on this, and then, like this wasn't published by the New York Times. This was published by some I forget some local newspaper. But there's a discussion on the New York Times that I'm linking to here, and I think that those people actually got fired for this map. So it's quite right. Yeah.
One question for me is like the size of the data points. It's useful for like the less populated areas, but when it gets like to that more populated areas that I don't know might be a little bit misleading.
Yeah, so like you can actually zoom in here. This is interactive, right? So you can zoom into your neighborhood and look exactly who around my house owns a gun. And so yes, like this is like at this scale, you don't see this in densely populated areas, but as we'll see in like the next couple of examples, where this tool went down, so this is not online anymore. This is just a screenshot that is very high level, and therefore I don't consider this chart here to be sensitive because it's so coarse. But you could actually zoom in all the way there. Here's like an XKCD version of basically a mix between isotypes and explicitly showing something. Here, each figure represents 250,000 voters. And it's kind of like an attempt at addressing the problem with the map that we showed, that I showed in the very first example. And you can see, of course, like population density is like there's a lot of people around the coasts, but not so many in the middle of the country. Yeah, I have some more examples, but that I've been into like a bit of a different category. I guess it's almost over, so I'll just continue here. Next time, and I'll see you guys on Tuesday.
Got 3D working. What's that? Got 3D working.